Let me show you these two learning paths side by side. On the left is the random scattered approach most aspiring data scientists take, jumping between Python, statistics, visualization tools, and machine learning algorithms without any structure. On the right is the systematic progression we're covering today. Notice how each skill builds upon the previous one in a logical sequence. This structured approach using Bloom's taxonomy ensures you're never overwhelmed because you're always building on a solid foundation. By the end of this video, you'll have a clear roadmap to transform how you learn data science from the ground up. Picture this. Two data scientists are presented with the same complex data set. The first one immediately starts applying various algorithms they've memorized, while the second takes a step back, examines the data structure, and asks fundamental questions about what the data actually represents. Who do you think will deliver more valuable insights? This distinction illustrates what separates a mere data practitioner from what experts like Alex Gutman call a data head. But what exactly is a data head? It's not just someone who can code in Python or create visualizations in Tableau. A data head thinks, speaks, and understands data at a fundamental level. They don't just know how to use tools, they comprehend why those tools work and when they should be applied. This mindset represents a profound shift in how we approach data science, moving beyond surface-level technical skills to develop a deep, intuitive understanding of data's underlying principles. The truth is, the data science landscape is evolving rapidly. While just a few years ago, familiarity with specific tools might have been enough to land you a job, today's employers are looking for something much more substantial. They want professionals who can think critically about data problems, not just apply prepackaged solutions. This evolution is reflected in current hiring trends across the industry. Companies are increasingly prioritizing candidates with strong conceptual understanding over those who simply list a catalog of programming languages on their resumes. The ability to understand statistical concepts and interpret data correctly has become more valuable than mere proficiency in Python or R. Consider this reality check. You can learn to use a new data visualization tool in a week, but developing the judgment to know what visualization best communicates your findings takes much longer. Similarly, you can memorize the syntax for implementing a machine learning algorithm, but understanding when that algorithm is appropriate and when it isn't requires deeper knowledge. The gap between tool-focused practitioners and concept-focused data scientists becomes most apparent when facing novel problems. When confronted with a dataset or challenge they haven't seen before, tool-focused professionals often struggle to adapt. They search for examples or tutorials that match their current situation, and when they can't find an exact match, they become stuck. By contrast, data heads thrive on novel challenges. Their foundational understanding allows them to decompose unfamiliar problems into familiar components. They can reason from first principles, adapting their approach to fit the unique characteristics of each new situation. This adaptability doesn't come from knowing more tools, it comes from understanding the underlying concepts that connect all data science problems. Think about it this way. Tools change constantly in the fast-moving field of data science. New libraries, frameworks, and platforms emerge every year. If your expertise is tied exclusively to specific tools, you'll find yourself in a perpetual cycle of catching up. But if your expertise is built on foundational knowledge, new tools simply become new ways to apply principles you already understand. Jose Miguel Cansado captures this perfectly when he states, "The most important skill of a data scientist is asking the right question to data." This insight underscores that the true value in data science comes not from executing procedures, but from knowing which questions will yield meaningful insights. And asking the right questions requires a deep understanding of data science fundamentals. This shift toward foundational knowledge is driving real changes in how companies evaluate and hire data talent. A study highlighted by Alex Gutman reveals that organizations now place greater emphasis on candidates who demonstrate solid grasp of statistical concepts and data interpretation skills rather than just familiarity with specific tools. The ideal candidate isn't someone who knows the most programming languages. It's someone who can approach problems creatively and effectively because they understand the underlying principles. Let's see how this plays out in a real scenario. Imagine a company wants to predict customer churn. A tool-focused practitioner might immediately implement a random forest algorithm because that's what they're familiar with. They might achieve decent results, but they would likely miss opportunities for improvement. A data head would approach the same problem differently. They would first consider whether this is truly a classification problem or if it might be better framed as a survival analysis. They would examine the distribution of the data to determine appropriate pre-processing steps. They would consider the business implications of different types of errors. Each decision would be informed by fundamental principles rather than habitual practices. This conceptual understanding creates a compounding advantage over time. While tool-focused practitioners must learn each new technique or algorithm as a separate entity, data heads can recognize patterns and similarities that allow them to grasp new concepts more quickly. They don't just accumulate knowledge, they integrate it into an evolving mental model of data science. The data head mindset also transforms how you communicate about data. When you understand concepts at a foundational level, you can explain complex ideas in simple terms. You can translate technical details into business implications. This communication skill becomes increasingly valuable as data science becomes more integrated with other business functions. What makes this mindset so crucial for your career trajectory in 2025 and beyond is that data problems are becoming more complex, not less. The low-hanging fruit of data science, the problems that can be solved with off-the-shelf solutions, are increasingly being automated. What remains are the challenging, nuanced problems that require creative thinking and deep understanding. This trend is already visible in the industry shift away from hiring generalist data scientists toward more specialized roles like machine learning engineers, analytics engineers, and decision scientists. Each of these roles requires specific domain expertise, but they all share a common foundation, a deep understanding of data fundamentals. The most compelling evidence for the value of the data head mindset comes from looking at career progression patterns. Professionals who invest in building strong foundations tend to advance more quickly into senior and leadership positions. They're better positioned to move across different domains and industries because their knowledge transfers more readily than tool-specific skills. As data continues to become central to more business functions, the ability to think critically about data will become valuable across virtually every role. The principles that data heads understand, statistical thinking, causal reasoning, dimensional analysis, are increasingly recognized as essential components of business literacy. This mindset serves as the foundation for everything that follows in your data science journey. It's the meta skill that enables all other data science skills to develop properly. Without it, you might become proficient in using certain tools, but you'll likely hit a ceiling in your effectiveness and career growth. Have you ever found yourself in a meeting where your data insights were solid, but you struggled to articulate them clearly? That ceiling in career growth often appears when you can think about data problems, but lack the precise language to communicate your insights. What separates those who merely use data tools from those who truly understand them isn't just technical skill. It's command of a specialized vocabulary that forms the neural network, connecting concepts in your mind and enabling collaboration with others. Bloom's taxonomy, a framework that classifies learning objectives, places knowledge acquisition at its foundation. This first level involves remembering facts, terms, and basic concepts. Without this foundation, advancing to higher level thinking becomes nearly impossible. In data science, this translates to building a robust technical vocabulary. The challenge for beginners is immediately apparent. The field presents an overwhelming lexicon spanning multiple domains. Statistics introduces terms like hypothesis testing, p-values, and confidence intervals. Programming brings objects, functions, and data structures. Machine learning adds algorithms, models, and hyperparameters. Each term represents not just a word to memorize, but a concept to internalize. Many aspiring data scientists make the critical mistake of approaching terminology as isolated facts to memorize rather than interconnected concepts. They might recognize that logistic regression is a classification algorithm, but fail to understand how it relates to linear regression, probability theory, or the broader family of generalized linear models. This disconnected knowledge creates fundamental gaps that become increasingly problematic as complexity increases. The difference between memorizing terms and understanding their relationships is like the difference between having individual puzzle pieces and seeing the complete picture. When you understand relationships, you can place new concepts within your existing knowledge framework, making them easier to recall and apply. Rather than learning that an algorithm is simply a set of instructions, you understand how it relates to models, how different algorithms serve different purposes, and how they connect to the broader data science workflow. A systematic approach to building technical vocabulary organizes terms by domain. Start with statistics as the fundamental language of data, covering descriptive statistics, probability distributions, and inferential methods. Next, add programming concepts organized by purpose rather than syntax, data structures, functions, and control flow. Finally, layer in machine learning terminology, from feature engineering to model evaluation metrics. This domain-specific organization creates natural contexts for remembering terms based on their functional relationships. Creating effective mental models means moving beyond simple definitions to understand how concepts connect. For instance, rather than learning regression, classification, and clustering as separate techniques, understand them as different approaches to pattern recognition with shared underlying principles. This networked understanding accelerates learning by allowing you to transfer knowledge between related concepts. When learning technical vocabulary, avoid the trap of studying terms in isolation. Instead, focus on relationships using techniques like concept mapping, where you visually represent connections between related terms. For example, a concept map for model evaluation might include branches for metrics like accuracy and precision, connecting to concepts like confusion matrices and ROC curves, while illustrating how these relate to different problem types. Spaced repetition represents another powerful technique for vocabulary acquisition. Rather than cramming terms before forgetting them, systematically review concepts at increasing intervals. Digital tools can track your familiarity with terms and schedule reviews just as you're about to forget them, strengthening neural pathways efficiently. This approach works particularly well for technical vocabulary because terms build upon each other hierarchically. Community engagement significantly enhances vocabulary acquisition. Participating in forums, study groups, and discussions forces you to articulate concepts, revealing gaps in your understanding. When you explain a statistical concept to someone else, you quickly discover whether you truly understand it or merely recognize the term. These interactions create emotional connections to learning that strengthen memory formation. Hands-on projects provide crucial context for vocabulary acquisition. Terms like overfitting remain abstract until you experience a model performing beautifully on training data but failing on new examples. The emotional impact of troubleshooting real problems embeds terminology in long-term memory more effectively than passive study. Each project should deliberately incorporate new terminology within practical contexts. Before advancing to more complex concepts, assess your vocabulary foundation through a technical vocabulary checkpoint. This self-assessment should cover core terms across domains. Can you explain the difference between correlation and causation? Do you understand what distinguishes supervised from unsupervised learning? Can you articulate what an algorithm actually does? These checkpoints reveal whether you have the language needed to progress or need to reinforce your foundation. The importance of this vocabulary foundation becomes evident in team contexts. When a colleague mentions they're concerned about multicollinearity in your regression model, you need to immediately understand the concept and its implications. Without shared terminology, collaboration becomes inefficient or impossible. In data science teams, miscommunications aren't just frustrating, they can lead to costly errors in analysis and interpretation. Technical vocabulary also enables efficient learning. When documentation refers to stochastic gradient descent or dimensionality reduction, immediate recognition of these terms allows you to focus on new information rather than getting stuck on terminology. The cognitive load of learning advanced concepts decreases dramatically when the basic vocabulary is automatic and intuitive. Beyond team communication, your vocabulary affects how stakeholders perceive your expertise. When presenting findings to non-technical audiences, your ability to translate complex concepts into accessible language while maintaining technical precision demonstrates mastery. This translation skill depends on thoroughly understanding the technical vocabulary yourself before simplifying it for others. Consider how essential terms form the foundation of data science communication. Algorithm isn't just a buzzword. It's a specific set of instructions that transforms inputs into outputs. Model represents a mathematical simplification of reality with particular assumptions and limitations. Data cleaning encompasses specific techniques for handling missing values, outliers, and inconsistencies. Feature engineering involves creating new variables that better represent underlying patterns. Machine learning distinguishes itself from traditional programming by improving performance from experience. Each term carries precise meaning that facilitates clear communication. The relationships between these terms create a mental framework that supports problem solving. When you understand that feature engineering influences model performance, that algorithms have biases related to their mathematical foundations, and that data cleaning affects statistical validity, you can navigate complex problems more effectively. These relationships form the language of data science thinking. The language of data science gives us the foundation, but there's a profound difference between being able to recite a definition and truly understanding its essence. Imagine being asked to explain how logistic regression works without using a single technical term. Would you struggle, or could you make it clear to someone with no background in data? This challenge reveals the critical gap between recognition and comprehension, a distinction that separates those who memorize terms from those who genuinely think like data scientists. While we've established the importance of building a robust technical vocabulary, we now need to explore the second level of Bloom's taxonomy, comprehension. This is where the transformation from information collector to analytical thinker begins. Comprehension is the bridge between merely knowing terminology and being able to use that knowledge effectively. Consider this example. When asked to define regression, a novice might correctly state, "It's a statistical method that examines relationships between variables." But when pressed to explain what that actually means or how to interpret regression output, they might stumble. They recognize the term but lack real understanding. True comprehension means you can explain the concept from multiple angles, identify its practical applications, and recognize its limitations. This distinction becomes especially important in statistics, where abstract concepts often hide behind familiar-sounding terms. Take the concept of statistical significance. Many can repeat that a p-value less than 0.05 is significant, but fewer understand what this truly indicates about the data or the limitations of this threshold. Surface-level recognition might get you through a multiple-choice test, but it won't help you make sound analytical decisions when the stakes are high. One of the most effective methods to verify your comprehension is what's often called the Feynman technique. Named after the renowned physicist Richard Feynman, this approach challenges you to explain a complex concept to a complete beginner, ideally a 10-year-old child. When forced to strip away technical jargon and complex notation, you quickly discover the areas where your understanding is solid and where it's superficial. For example, could you explain how a classification algorithm makes decisions without using terms like decision boundary or probability threshold? The process of simplifying forces you to confront gaps in your knowledge that jargon might have been concealing. If you can't explain it simply, you haven't understood it well enough. Complete comprehension in data science requires understanding across three interconnected domains. First, there's the mathematical domain, understanding the underlying equations, their derivations, and their implications. Second is the computational domain, knowing how these mathematical ideas are implemented in code and the practical considerations involved. Third is the business context, understanding when and why to apply these techniques and how to interpret results for decision making. Most data professionals are stronger in one or two of these domains than in others. Some excel at the mathematical theory, but struggle to translate that into working code. Others are coding wizards, but can't explain the business implications of their results. True comprehension means developing fluency across all three domains and seeing how they connect. So, how do you identify gaps in your understanding? Self-questioning techniques are remarkably effective. When learning about a new concept, don't just ask, "Do I know what this is?" Instead, push deeper with questions like, "Can I derive this formula from first principles?" What assumptions does this technique make about the data? Under what circumstances would this approach fail? What are the alternatives to this method, and when would I choose each one? How would I explain this result to a non-technical stakeholder? Questions like these reveal the boundaries of your understanding and highlight areas needing more attention. They transform passive learning into active investigation. For deepening your comprehension, visualization stands as one of the most powerful strategies. Our brains are wired to process visual information more efficiently than abstract concepts. Effective data visualizations can transform complex statistical relationships into intuitive insights, making them accessible not just to others but to yourself as well. When you can visualize how data points cluster or how a decision boundary separates classes, abstract mathematical concepts become concrete. Another powerful strategy involves using analogies to bridge the gap between the unfamiliar and the familiar. For instance, explaining algorithms through everyday tasks can illuminate their step-by-step nature. Consider how you might explain the concept of an algorithm using the process of making a peanut butter sandwich. Each instruction must be precise and in the correct order for the desired outcome. This type of analogy helps transform abstract computational thinking into concrete understanding. First principles thinking also enhances comprehension by breaking complex ideas down to their fundamental truths and rebuilding from there. Instead of accepting a machine learning technique as a black box, understanding it from first principles means grasping the core mathematical concepts it's built upon, the problems it was designed to solve, and how its components work together. To structure your journey toward deeper comprehension, consider establishing specific checkpoints for key concepts. For regression, a comprehension checkpoint might include being able to explain the difference between correlation and causation, interpreting regression coefficients in plain language, and recognizing when linear assumptions are violated. For classification, it might include understanding decision boundaries, explaining trade-offs between precision and recall, and knowing when to use different classification metrics. Case studies reveal how this recognition versus comprehension gap manifests in practice. A student might recognize the term regression, but still fail to explain its application or significance in a real-world scenario. They might know that regression finds relationships between variables, but can't articulate how to use regression results to make predictions or business decisions. This gap between recognition and comprehension frequently appears when students are asked to apply their knowledge to new situations. The relationships between concepts also deepen comprehension. Understanding how regression relates to classification, for instance, provides a mental framework that supports problem solving. When you grasp that both are supervised learning techniques but approach prediction differently, you can make more informed choices about which to apply in specific situations. True comprehension transforms abstract concepts into intuitive mental models that you can manipulate and apply flexibly. When you genuinely understand a concept, you no longer need to memorize steps or formulas. Instead, you can reason through problems from first principles, adapting your approach as needed. You develop a feel for the data and can anticipate how different techniques will perform without having to try each one. This level of comprehension doesn't happen overnight. It requires deliberate practice, curiosity, and willingness to question your assumptions. It means going beyond tutorials and asking why at each step. It requires connecting new knowledge to existing understanding, creating an ever-expanding web of interrelated concepts rather than a collection of isolated facts. That deliberate practice mentioned earlier becomes transformative when applied to real-world projects. Consider this paradox. You need experience to get a data science job, but you need a job to get experience. Breaking this cycle requires a strategic approach to project-based learning that separates successful candidates from the perpetually job hunting. Welcome to the third level of Bloom's taxonomy application. This is where theory meets practice, where abstract understanding transforms into tangible skills. While comprehension is essential, employers aren't hiring you for what you know. They're hiring you for what you can do with that knowledge. The transition from understanding concepts to applying them represents a critical developmental step in your data science journey. It's also where many aspiring data scientists get stuck. You've learned the mathematical foundations of algorithms. You understand how regression models work in theory, but can you implement them to solve real problems with messy data? The application phase is where you'll encounter the classic catch-22 of the job market. Companies want candidates with experience, but how do you gain experience without first getting hired? This frustrating cycle leaves many qualified individuals spinning their wheels, endlessly consuming tutorials without building the practical portfolio that would demonstrate their capabilities. The solution lies in creating your own experience through a carefully structured progression of hands-on projects. This progression typically begins with guided tutorials, but must quickly advance beyond them. Let me explain why tutorials alone won't get you hired. Tutorials serve as training wheels, useful for getting started, but ultimately limiting. They provide a scaffolded environment where every step is predetermined, data is pre-cleaned, and problems are carefully selected to demonstrate particular techniques. This controlled environment bears little resemblance to the messy reality of actual data science work. The difference between completing tutorials and building projects from scratch is comparable to the difference between following a cooking recipe and creating your own dish. Following a recipe demonstrates basic competence, but creating a successful original dish demonstrates true culinary understanding. Similarly, employers want to see evidence that you can approach unfamiliar problems without step-by-step instructions. When you move beyond tutorials, you'll face new challenges, identifying appropriate data sources, determining which cleaning steps are necessary, selecting relevant features, choosing suitable models, and validating your results, all without an instruction manual. This unstructured process is precisely what builds the critical thinking and problem-solving abilities that employers value most. The transition from tutorial follower to independent project creator happens gradually through what we might call tutorial modification. Begin by completing a tutorial as written, then challenge yourself to extend it. Can you apply the same technique to a different dataset? Can you improve the model's performance by trying different parameters? Can you visualize the results more effectively? Each modification builds confidence in your ability to work without explicit guidance. As you gain confidence, you'll be ready to create portfolio projects that showcase specific skills. Effective portfolio projects share several key characteristics. First, they demonstrate clear business value rather than technical showmanship. Instead of implementing the latest complex algorithm to impress technical reviewers, focus on showing how your work solves meaningful problems. Personal projects analyzing your own data can be particularly effective in demonstrating both technical skills and genuine interest. For example, creating a recommendation system using your own Spotify listening history not only showcases your technical abilities, but also communicates authenticity and personal engagement with the work. This combination of technical competence and genuine interest makes your portfolio memorable to potential employers. The concept of deliberate practice becomes especially relevant in this phase of your development. Unlike passive learning or simply accumulating experience, deliberate practice involves focused, repetitive work on specific skills with the explicit goal of improvement. In the context of data science, this means identifying your weakest areas and designing projects specifically to strengthen them. The concept of deliberate practice becomes especially relevant in this phase of your development. Unlike passive learning or simply accumulating experience, deliberate practice involves focused, repetitive work on specific skills with the explicit goal of improvement. In the context of data science, this means identifying your weakest areas and designing projects specifically to strengthen them. For instance, if you struggle with feature engineering, you might create a project where the primary challenge involves transforming raw variables into more predictive features. If your weakness lies in data visualization, you could focus on a project that requires communicating complex findings through intuitive graphics. Each project becomes an opportunity to target specific skills for improvement. Structuring your projects to showcase both technical competence and problem-solving ability requires conscious attention to documentation and presentation. Your code should be clean, well-commented, and organized logically. Your README file should clearly articulate the problem you're solving, your approach, the results you achieved, and the insights you gained. Presentation matters almost as much as the technical work itself. If employers can't understand what you've done, they can't appreciate its value. The most effective portfolio projects also demonstrate your ability to complete the full data science workflow. Problem formulation, data collection, exploratory analysis, feature engineering, modeling, evaluation, and communication of results. Many aspiring data scientists focus exclusively on modeling, neglecting crucial steps like exploratory analysis and result interpretation. A comprehensive project that addresses all these phases demonstrates a mature understanding of the entire process. While building a portfolio, remember that quality matters more than quantity. 3 thoughtfully executed, well-documented projects that demonstrate different skills will impress employers more than a dozen hastily completed exercises. Each project should tell a story that highlights your unique strengths and approach to problem solving. Self-taught data scientists have particular opportunities to demonstrate initiative through projects that analyze interesting datasets or create applications solving real-world problems. Whether you're analyzing public datasets from sources like Kaggle or creating your own datasets by scraping websites or accessing APIs, these projects demonstrate your ability to work independently, a quality highly valued in data science roles. The quality of your portfolio significantly impacts hiring decisions. Employers prioritize candidates who can demonstrate relevant projects that show both technical skills and an understanding of business context. This is especially true for candidates without formal credentials or industry experience, where portfolio projects become the primary evidence of capability. The most impressive portfolios don't just demonstrate technical skills, they communicate business value. For each project, clearly articulate not just what you did, but why it matters. How would your analysis or model benefit an organization? What decisions could be made based on your insights? Connecting your technical work to business outcomes demonstrates the mature understanding that separates leading candidates from the crowd. As you build your portfolio, consider developing projects that showcase different aspects of your skill set. One project might demonstrate your ability to clean and pre-process messy data. Another might showcase sophisticated visualization techniques that make complex patterns accessible to non-technical audiences. A third might highlight your machine learning expertise through model development and evaluation. Together, these diverse projects create a comprehensive picture of your capabilities. Remember that application-level mastery doesn't happen instantly. Each project will present unique challenges that develop different aspects of your skill set. Embrace these challenges rather than avoiding them. The difficulties you encounter in independent projects are precisely what build the problem-solving muscles that employers value. Those problem-solving muscles you've developed through independent projects are now ready for a more sophisticated challenge: analysis. When confronted with a complex data set, the critical question isn't just, how do I implement this technique, but rather, which technique should I apply in the first place? This analytical decision-making separates novice practitioners from true data scientists. Analysis represents the fourth level of Bloom's taxonomy, where we move beyond simply applying techniques to understanding when, why, and how to use them appropriately. Think about it. Facing a new dataset, you might have over 15 different analytical approaches that could potentially apply. How do you systematically determine which one will extract the most valuable insights? The paradox that many data scientists face is that the same dataset can tell completely different stories depending on which analytical lens you apply. This isn't a trivial challenge, it's the essence of analytical thinking in data science. Let me illustrate with a scenario. Imagine you have customer purchase data from an e-commerce platform. A regression analysis might reveal how factors like advertising spend correlate with sales, leading to one set of business recommendations. However, a clustering analysis of the same dataset could identify distinct customer segments based on purchasing behavior, pointing to entirely different strategic opportunities. The abundance of analytical approaches can be overwhelming. Beyond the familiar categories of supervised and unsupervised learning, we have regression, classification, clustering, dimensionality reduction, association rule learning, reinforcement learning, natural language processing, computer vision, algorithms, and within each of these categories, dozens of specific implementations. No wonder many aspiring data scientists freeze when faced with this decision. What's needed is a structured decision framework for selecting analytical techniques. This framework should begin with a fundamental question: what type of problem are you solving? If you're predicting a continuous outcome, like housing prices or sales figures, regression techniques may be appropriate. If you're predicting categories or classes, like customer churn or email spam, classification approaches make more sense. If you're trying to discover natural groupings in your data without predefined labels, clustering becomes relevant. The framework continues by considering the characteristics of your data set. The size and quality of your data will directly influence which techniques are viable. Machine learning approaches often require larger datasets to perform effectively, while simpler statistical methods may be sufficient for smaller samples. Similarly, the presence of missing values, outliers, or imbalanced classes will further narrow your analytical options. But the most overlooked aspect of this decision framework is context. Understanding the business goals and specific questions to be answered is paramount. Without this clarity, you risk conducting technically sound analyses that fail to deliver actionable insights. Before diving into technique selection, ask, what decisions will be made based on this analysis? What actions might result? What level of accuracy or explainability is required? These contextual considerations should guide your analytical approach from the start. Beyond the decision framework, there are critical analytical skills that every data scientist must develop. Pattern recognition tops this list, the ability to identify recurring structures or trends within complex data sets. This isn't just about spotting the obvious. It's about recognizing subtle patterns that might indicate underlying phenomena worthy of investigation. Equally important is anomaly detection, identifying data points that deviate significantly from the norm. These outliers sometimes represent errors that need cleaning, but they can also reveal valuable insights or edge cases that deserve special attention. The analytical skill lies in distinguishing between meaningless noise and significant anomalies that tell an important story. The third critical skill is relationship identification, discerning how variables interact with each other. This extends beyond simple correlation to understanding potential causal relationships, interaction effects, and hierarchical dependencies. Mastering this skill enables you to build more sophisticated models that capture the true complexity of real-world phenomena. To apply these skills effectively, you need a systematic process for dataset analysis. This process begins by defining the problem clearly, then moves to collecting relevant data, followed by cleaning and preparation. Only then do you select appropriate analytical techniques based on your decision framework. The final steps involve interpreting results and, crucially, revisiting earlier steps as new insights emerge. This iterative nature of data analysis cannot be overstated. Initial findings frequently lead to new questions and deeper investigations. You might start with exploratory data analysis using simple visualization techniques, discover an unexpected correlation, and then apply more sophisticated methods to investigate further. Each iteration refines your understanding and improves your analytical approach. Let me demonstrate how this works in practice. Consider a data set on housing prices. Your initial exploratory analysis might reveal a nonlinear relationship between house size and price. This observation would lead you away from simple linear regression toward more flexible models. You might then discover distinct neighborhood clusters that influence pricing differently, suggesting a hierarchical or segmented modeling approach. Each analytical decision builds on previous insights in an iterative fashion. Different analytical techniques applied to the same dataset can yield remarkably different insights. A time series analysis of stock prices might focus on seasonal patterns and trend projections, while a sentiment analysis of news coverage about those same stocks could reveal how public perception influences market movements. Neither approach is inherently superior. They simply answer different questions using the same underlying data. To ensure you're on the right analytical track, establish checkpoints throughout your process. Before implementing any technique, verify that it aligns with your problem definition, data characteristics, and business context. Ask yourself, does this approach address the core question? Is it appropriate given my dataset size and quality? Will the results be interpretable and actionable for stakeholders? These checkpoints prevent wasted effort on technically impressive but practically irrelevant analyses. One particularly valuable checkpoint is the technique justification test. Can you clearly articulate why you chose a particular analytical approach over alternatives? If not, you may be relying on familiarity rather than fitness for purpose. The most elegant machine learning algorithm is useless if a simple statistical test would better answer the question at hand. For complex analytical challenges, consider a technique comparison approach. Apply multiple methods to the same problem and compare their results. This not only provides richer insights, but also builds confidence in findings that appear consistently across different analytical lenses. When different approaches yield contradictory results, you've discovered a valuable area for deeper investigation. The practical application of analytical decision-making extends beyond technique selection to implementation details. For example, when using regression analysis to predict housing prices, you might need to decide between linear regression, polynomial regression, or more advanced approaches like gradient boosting. This secondary level of analytical decision-making requires both technical knowledge and practical judgment. A case study illustrates this perfectly. Researchers working on housing price prediction found that combining multiple analytical techniques, regression analysis with machine learning methods, produced more accurate results than either approach alone. This multifaceted approach to data analysis is increasingly common in sophisticated data science work, where single technique solutions rarely capture the full complexity of real-world problems. What if the true power of data science lies not in mastering individual methods, but in orchestrating them into harmonious solutions? The housing price prediction case study we discussed earlier reveals just the tip of the iceberg. When we examine how Alex Gutman approached this challenge, we discover something fascinating. He didn't simply apply one technique and call it a day. Instead, he strategically integrated multiple methodologies, first establishing a foundation with regression analysis before enhancing it with machine learning approaches to capture more complex patterns in the data. This brings us to synthesis, the fifth level of Bloom's taxonomy, where we move beyond analyzing individual components to combining elements into new, more powerful patterns. This is where data science truly comes alive. Most data science courses teach techniques in isolation. Here's linear regression, there's random forests, now try gradient boosting. But in practice, real-world problems rarely conform neatly to single methodologies. The experienced practitioner doesn't just know how to apply individual tools. They understand how to weave them together into solutions far greater than the sum of their parts. Consider what it means to be a solution architect in the data science realm. Unlike beginners who might instinctively reach for their favorite algorithm, perhaps the one they're most comfortable with, seasoned professionals start by mapping the entire problem space before determining which combination of tools will address all dimensions of the challenge. This architectural mindset shifts the focus from techniques to outcomes, from tools to solutions. So, how do you recognize when a problem requires multiple techniques? There are several telltale signs. First, when your data exhibits different characteristics across segments, perhaps linear relationships in some areas, but nonlinear in others. Second, when you're balancing competing priorities like accuracy versus interpretability, where no single method satisfies both requirements. Third, when your problem involves multiple steps in a pipeline, each demanding specialized approaches. The synthesis phase demands that you understand not just how individual techniques work, but how they can complement each other. It's about recognizing the strengths and limitations of each method and strategically combining them to mitigate weaknesses. This requires a mental model of your entire analytical toolkit, seeing connections between seemingly disparate approaches. Let me share a concrete example of effective synthesis. In financial fraud detection, Simple rule-based systems can quickly identify obvious cases, while sophisticated anomaly detection algorithms catch subtler patterns, but neither approach alone provides optimal results. The rule-based system misses sophisticated fraud attempts, while the complex algorithm generates too many false positives and operates as a black box that's difficult to explain to regulators. The solution? An integrated approach that applies rules as a first-pass filter, feeds borderline cases to machine learning models for deeper analysis, and then subjects the machine learning results to a statistical validation framework that ensures findings are robust. This synthesized approach achieves higher accuracy than any single method while maintaining interpretability, something critical in regulated industries. Another powerful form of synthesis emerges through ensemble methods, which combine multiple models to improve predictive performance. Techniques like bagging, bootstrap aggregating, and boosting demonstrate how integrating various models can achieve results superior to any individual model. These approaches formalize the process of synthesis into methodological frameworks that can be systematically applied, but how do you know if your synthesized approach actually works? This requires evaluation frameworks specifically designed for integrated solutions. Cross-validation becomes particularly important, ensuring that your combined approach generalizes well to unseen data rather than just fitting the peculiarities of your training set. Beyond accuracy metrics, you'll want to assess both the interpretability of your solution and its computational efficiency. A sophisticated synthesis that takes days to run may be theoretically elegant, but practically useless. Performance metrics must be multidimensional, evaluating not just the final output, but the contribution of each component to the whole. When Goodman combined statistical methods with machine learning in his housing price prediction model, he didn't just measure overall accuracy, he specifically quantified how much improvement came from each additional technique in his integrated approach. Developing this synthesis skill doesn't happen overnight. It emerges through experience, particularly as you encounter diverse problems that expose the limitations of single technique approaches. Each time you face a challenge where your go-to method falls short, you're forced to expand your toolkit and consider how different approaches might work together. To accelerate this development, I recommend creating synthesis checkpoints in your workflow. After analyzing your problem and selecting potential techniques, explicitly ask, what aspects of this problem might one approach miss that another could capture? And how could these methods work together rather than in competition? This intentional pause forces you to consider integration possibilities before diving into implementation. Another effective practice is to deliberately implement multiple approaches to the same problem, even when your initial analysis suggests one method would be sufficient. This parallel implementation often reveals unexpected insights about where different techniques excel or struggle, building your intuition for future synthesis opportunities. The synthesis phase also introduces a crucial shift in how you organize your code and analytical process. Rather than building monolithic solutions, you'll develop modular components that can be combined, reconfigured, and extended. This architectural thinking extends beyond the analytical techniques themselves to encompass your entire workflow, from data preparation to visualization and communication. Consider creating a personal library of technique combinations that have proven effective for certain problem classes. Much like a chef develops signature flavor combinations through experimentation, you'll discover synthesis patterns that become part of your professional signature. These might include specific pre-processing steps paired with particular algorithms, or novel ways of blending predictions from different model families. One particularly powerful synthesis approach involves combining domain-specific statistical methods with general-purpose machine learning algorithms. The statistical methods encode known relationships and domain knowledge, while the machine learning components capture unexpected patterns and interactions. This marriage of theory-driven and data-driven approaches often produces superior results compared to either paradigm alone. This isn't just theoretical. Organizations increasingly expect this level of sophistication. Projects that might once have been tackled with a single regression model now require thoughtful integration of multiple techniques, often spanning traditional statistics, machine learning, and sometimes even operations research or network analysis. The ability to navigate this complexity and synthesize cohesive solutions represents a competitive advantage in the job market. What separates successful data science projects from those that collect digital dust? Nearly 85% of data science initiatives fail to make it to production despite being technically flawless. This staggering failure rate reveals a critical truth. Technical excellence alone doesn't guarantee business impact. Consider Amazon's AI recruiting tool that had to be abandoned after it began systematically discriminating against women candidates. The algorithm was well built from a technical perspective, but the team failed to properly evaluate its real-world implications before deployment. This costly mistake represents just one of countless examples where sophisticated data science work never delivered actual value. We've now reached the 6th level of Bloom's taxonomy, evaluation. This level represents the ability to make critical judgments about the quality, validity, and value of data science work. While previous levels built your capacity to understand and create solutions, evaluation focuses on your ability to critique those solutions rigorously and ensure they deliver genuine business value. The gap between technically correct work and valuable outcomes is often wider than most practitioners realize. A model can achieve impressive accuracy metrics while completely missing the business objective it was meant to serve. For instance, a fraud detection algorithm might boast 99% accuracy while failing to identify the most costly types of fraud that actually matter to the business. Without proper evaluation frameworks, these disconnects remain invisible until it's too late. Effective evaluation in data science must occur across multiple dimensions simultaneously. First, we need to assess technical validity. Does the model actually do what we claim it does? Second, we must examine fairness and bias. Does the model perform equally well across different groups? Third, we need to measure business impact. Does the model solve the problem in a way that creates real value for the organization? Let's break down these critical evaluation skills further. Validity assessment involves rigorously testing your work against appropriate benchmarks and ensuring it generalizes beyond your training data. This means not just looking at overall accuracy, but examining how your model performs on specific subsets of data that matter most to the business objective. For instance, if you're building a customer churn prediction model, evaluating performance on high-value customers might be more important than overall accuracy. A model that predicts correctly for 90% of customers, but misses the 10% who generate 80% of revenue isn't actually very useful despite its seemingly impressive metrics. Bias detection has become increasingly crucial as organizations recognize the ethical and business risks of deploying biased models. This involves analyzing how your model performs across different demographic groups and employing fairness metrics to identify potentially discriminatory patterns. Techniques for detecting bias include examining the distribution of predictions across different groups and testing whether your model systematically favors certain outcomes for particular segments. Impact measurement moves beyond technical metrics to assess how your work affects business outcomes. This requires translating model performance into business metrics that stakeholders care about: revenue generated, costs saved, or risks mitigated. Without this translation, technically impressive work often fails to demonstrate its value. To systematically critique your own work before presenting it to stakeholders, I recommend a three-stage evaluation process. First, conduct a technical review where you challenge assumptions, test edge cases, and verify methodology. Second, perform an ethical review examining potential biases, unintended consequences, and privacy implications. Finally, conduct a business review assessing alignment with objectives, expected ROI, and implementation feasibility. Let me share a real-world example of a technically impressive project that failed due to poor evaluation. A retail company invested heavily in developing a sophisticated customer segmentation model using advanced clustering algorithms. The data science team was proud of their technical achievement. The model elegantly identified distinct customer groups with clear mathematical separation. However, when the marketing team tried to use these segments to design targeted campaigns, they discovered the model had created groupings that made little sense from a business perspective. The clusters were mathematically elegant, but practically useless because the evaluation process never examined whether the segments would enable actionable marketing strategies. Months of work and substantial investment yielded no business value. This is why formal evaluation checkpoints are essential throughout the data science workflow. These checkpoints create structured moments to assess both the process and outcomes of your work. Process checkpoints might include data quality validation, methodology review, and assumption testing. Outcome checkpoints examine performance metrics, stakeholder feedback, and business impact assessments. One particularly valuable framework involves predefined evaluation metrics that assess projects at critical junctures. These metrics should be established at the project's outset with stakeholder agreement, ensuring alignment between technical work and strategic objectives. For example, a loan approval model might be evaluated on both predictive accuracy and fairness across demographic groups, with specific thresholds established for both metrics. A structured approach to evaluation also improves your ability to communicate effectively with stakeholders. By translating complex technical findings into frameworks that address business concerns directly, you bridge the gap between data science work and organizational decision-making. This is particularly important as projects move from development to implementation, where stakeholder buy-in becomes crucial. The skills of validity assessment, bias detection, and impact measurement don't come naturally to most technically oriented practitioners. Many data scientists excel at building models but struggle to critically evaluate their own work. Developing this capacity requires deliberate practice and a willingness to challenge your own assumptions. Start by inviting constructive criticism from colleagues with different perspectives. Business analysts, subject matter experts, and end users can all identify weaknesses in your approach that you might miss. Create formal review sessions where your work is systematically challenged from multiple angles. Another powerful evaluation technique is scenario testing, where you imagine different real-world conditions and assess how your model would perform. Would your recommendation algorithm still work if user preferences suddenly shifted? Would your forecasting model handle a black swan event? These thought experiments reveal fragilities in your approach that technical metrics might miss. Ethical considerations should feature prominently in your evaluation framework. As data science applications increasingly affect people's lives, scrutinizing potential harmful impacts becomes essential. Ask whose interests are served by your model and whose might be harmed. Consider whether your work might inadvertently reinforce existing inequalities or create new ones. The case of Amazon's biased recruiting algorithm highlights why technical evaluation alone isn't sufficient. The team likely focused on metrics like prediction accuracy while failing to detect the systematic gender bias their model had learned from historical hiring data. Proper evaluation would have included tests for bias across protected characteristics, saving the company from an embarrassing and costly mistake. Developing strong evaluation skills requires humility. The recognition that even technically sophisticated work can fail to deliver value if it doesn't address the right problem or considers only narrow success criteria. This humility must be balanced with confidence in defending your work against invalid criticisms. Not all stakeholder feedback carries equal weight, and sometimes you'll need to explain why certain technical choices are necessary despite seeming counterintuitive. The technical evaluation skills we've discussed are crucial, but they represent only half the battle. What separates truly influential data scientists from mere technical experts isn't their analytical prowess, it's their ability to translate complex insights into language that drives action across different organizational contexts and audiences. Think about it. How often have you seen brilliant analyses gather dust because no one understood their significance? The gap between technical discovery and business action costs organizations billions annually in wasted analytics investments. The most sophisticated model in the world delivers zero value if it can't be explained to the people with decision-making authority. Communication is the bridge that transforms technical excellence into organizational impact. While your technical skills might impress fellow data scientists, your communication skills determine whether your work actually changes anything in the real world. The disconnect between technical practitioners and business stakeholders often stems from fundamentally different mental models. Data professionals think in distributions, probabilities, and algorithms. Business stakeholders think in opportunities, risks, and bottom-line impacts. When these worlds collide without proper translation, the result is confusion, frustration, and ultimately inaction. Consider what happens in these cross-functional meetings. Technical teams proudly present their methodological rigor and statistical significance, while business stakeholders silently wonder, what does this mean for our quarterly targets? Both sides leave feeling misunderstood and questioning the value of the collaboration. Bridging this gap requires mastering 3 distinct communication modes, each serving a different purpose in your data storytelling arsenal. First, technical documentation captures the methodological details and implementation specifics needed for peer review and reproducibility. While critical for knowledge transfer among technical team members, this mode is rarely appropriate for broader audiences. The second mode, executive summaries, distills complex findings into concise business implications. These communications strip away technical complexity to highlight key insights, recommendations, and expected impacts. The focus shifts from how we analyzed to what we discovered and why it matters. The third mode, visual storytelling, transforms abstract data into compelling narratives that engage stakeholders emotionally as well as intellectually. This approach leverages our innate ability to process visual information and follow narrative structures, making complex insights accessible to diverse audiences. The key to effective data communication lies in adapting your approach based on your audience's technical literacy, decision-making authority, and information needs. Before preparing any presentation or report, ask yourself, who exactly is my audience? What decisions will they make with this information? What level of technical detail will help rather than hinder their understanding? For technical peers, you might emphasize methodological innovations and statistical nuances. For operational managers, focus on actionable insights that improve specific processes. For executives, highlight strategic implications, competitive advantages, and bottom-line impacts. The medium itself should also match your audience's preferences. Some stakeholders absorb information best through interactive dashboards, others through brief written summaries, and still others through in-person conversations where they can ask questions freely. Effective data visualization stands as perhaps the most powerful tool in your communication toolkit. When done properly, visualization transforms abstract numbers into intuitive patterns that even non-technical audiences can grasp immediately. However, Creating truly effective visualizations requires more than technical proficiency with plotting libraries. The best visualizations prioritize clarity over complexity. They highlight key insights rather than overwhelming viewers with exhaustive detail. They use appropriate chart types based on the relationship being illustrated. Line charts for trends over time, bar charts for comparisons between categories, and scatter plots for relationship patterns between variables. Color, when used strategically rather than decoratively, can direct attention to critical information. Annotations that explain unusual data points or highlight key thresholds can transform a static visualization into a guided analytical experience. And titles that state the conclusion rather than merely describing the content ensure viewers don't miss the forest for the trees. But individual visualizations, no matter how clear, only become truly powerful when woven into cohesive data narratives. Effective data storytelling follows a structure that guides audiences from curiosity to comprehension to action. Start by establishing context that connects to your audience's existing priorities. Present your key findings in a logical sequence that builds toward your main conclusion. Then translate those findings into specific recommendations that stakeholders can act upon. For instance, rather than simply reporting that customer churn increased by 8% last quarter, frame this insight within a narrative. Our analysis revealed that customers who experience more than 2 service disruptions are 3 times more likely to cancel their subscriptions. This suggests that improving service reliability could reduce our churn rate by approximately 8%, potentially recovering $1.2 million in annual recurring revenue. This narrative approach accomplishes several things simultaneously. It connects the raw data to a cause and effect relationship, quantifies the business impact, and points toward a specific intervention, all elements that make the insight actionable for decision makers. Developing a framework for structuring these narratives can help ensure consistent effectiveness. One proven approach follows the situation complication resolution pattern. Begin by establishing the current situation and business context. Introduce the complication or challenge revealed by your analysis. Then present your resolution in the form of insights and recommendations. Another effective framework uses the what so what now what structure. First, present what you found, the data. Then explain so what it means, the implications. Finally, recommend now what should be done, the actions, regardless of which framework you choose. Always frame your communication around the decisions your analysis aims to inform. Data insights divorced from decision contexts rarely drive meaningful action. By starting with the decision in mind, you ensure your communication remains focused on what matters most to stakeholders. Of course, even the most carefully crafted communication can miss its mark. That's why incorporating feedback loops and communication checkpoints into your process is essential. These verification points help ensure your message is landing as intended with your target audience. Simple techniques like having a non-technical colleague review your presentation before delivering it to stakeholders can reveal jargon and assumptions that might otherwise create barriers to understanding. Watching facial expressions and body language during presentations provides real-time feedback on audience engagement and comprehension. And following up after presentations with questions about what resonated and what remained unclear helps refine future communications. More formal checkpoints might include stakeholder interviews to understand how your insights influence their thinking, tracking which recommendations were implemented, and measuring whether those implementations delivered the predicted outcomes. These feedback loops not only improve your communication effectiveness, but also strengthen your analytical processes by revealing blind spots in your approach. One particularly valuable checkpoint involves asking stakeholders to explain your findings in their own words. The gaps between your intended message and their understanding highlight precisely where your communication needs refinement. Communicating effectively with stakeholders bridges the gap between analysis and action, but there's another dimension that elevates data science work from merely competent to truly exceptional. Have you noticed how some data scientists consistently generate more innovative solutions than others with similar technical skills? The difference often lies in their ability to see beyond individual techniques to understand how different domains interconnect and influence each other, what experts call systems thinking. When you ask stakeholders to explain your findings in their own words, you're actually doing something profoundly important, testing whether your isolated analysis connects to their broader business ecosystem. This ability to connect isolated components into a coherent whole represents the pinnacle of data science expertise. Systems thinking views data science not as a collection of separate tools and techniques, but as an interconnected ecosystem where each component influences and is influenced by others. Rather than seeing statistics, machine learning, and data engineering as distinct disciplines, systems thinkers recognize how these domains interact and complement each other. This holistic perspective allows them to approach complex problems with a more comprehensive understanding of potential solutions. Consider how a systems thinker approaches a customer churn prediction project, while a technically proficient but narrowly focused data scientist might immediately jump to building a predictive model using historical customer data. A systems thinker first examines how customer interactions flow through various company touchpoints. They consider how marketing campaigns influence customer sentiment, how product usage patterns reflect customer satisfaction, and how customer service interactions shape retention. By understanding these interconnections, they can design a solution that integrates multiple data sources and methodologies, producing insights that reflect the full complexity of customer behavior. This integrated perspective stands in stark contrast to how beginners typically approach data science problems. Novices often view each technique as a separate tool to be applied in isolation. I'll use linear regression for this problem. K means clustering for that one, and maybe a random forest for another. They struggle to see how these techniques complement each other or how insights from one domain might inform approaches in another. The ecosystem view enables data scientists to create solutions that transcend individual methodologies. As one project demonstrated, analyzing social media data to predict public sentiment around political events proved significantly more accurate when various data sources were integrated rather than analyzed in isolation. The systems thinker recognizes that the boundaries we create between different data domains are often artificial constructs that can limit our thinking. Curiosity, empathy, and creativity form the foundation of systems thinking in data science. As Alex Gutman notes, the key to turn data into insight lies in what we can do that machines can't yet: curiosity, empathy, and creativity. This human element allows systems thinkers to ask questions that algorithms cannot formulate on their own, to understand the needs and perspectives of various stakeholders, and to envision novel combinations of techniques that might address complex challenges. To develop systems thinking skills, start by visualizing the relationships between different data science domains. Create concept maps that show how statistical methods connect to machine learning algorithms, how data engineering practices influence analytical capabilities, and how business context shapes both the questions we ask and the interpretations we generate. These visual frameworks help transform a fragmented understanding into a coherent whole. One practical exercise involves taking a recent project and deliberately identifying connections to other domains that weren't initially considered. For instance, if you've conducted a regression analysis to understand factors affecting product sales, explore how machine learning techniques might enhance your predictions, how data visualization principles could make your findings more accessible to stakeholders, and how business strategy considerations might alter the question you originally posed. Systems thinking also helps data scientists navigate the rapidly evolving technological landscape. When you understand the underlying principles that connect different tools and techniques, learning new technologies becomes less about mastering isolated skills and more about integrating new capabilities into your existing knowledge framework. This makes adaptation to emerging technologies significantly more efficient. Let's look at how this plays out in practice. Imagine a data project that aims to predict customer lifetime value. A systems thinker would recognize that this challenge requires statistical knowledge to understand probability distributions of customer spending, machine learning expertise to build predictive models, data engineering skills to integrate various customer data sources, business acumen to define meaningful customer segments, and communication abilities to translate findings into actionable insights for marketing teams. By seeing these interconnections, they can design a comprehensive approach that leverages strengths from each domain. This holistic understanding also helps identify potential pitfalls that might not be apparent from a narrow perspective. For instance, a systems thinker would recognize how biases in data collection could propagate through an analysis pipeline, how statistical assumptions might influence machine learning model performance, and how organizational constraints might impact the implementation of analytical findings. This broader awareness leads to more robust and reliable outcomes. To verify your development of systems thinking abilities, establish checkpoints that assess your holistic understanding. Can you articulate how different components of your data project influence each other? Can you explain how changes in one aspect of your analysis might ripple through other elements? Can you identify connections between seemingly unrelated data domains that might yield innovative approaches? If you can confidently answer these questions, you're developing the systems perspective that characterizes expert data scientists. Organizations increasingly recognize the value of systems thinking in data science. Case studies consistently show that data teams employing systems approaches achieve better outcomes than those working in disciplinary silos. For example, combining statistical analysis with machine learning techniques can significantly improve predictive accuracy compared to either approach used in isolation. This complementary relationship between different methodologies exemplifies the power of integrated thinking. Systems thinking also enhances collaboration across diverse teams. When data scientists understand how their work connects to the contributions of data engineers, business analysts, and other stakeholders, communication becomes more effective and projects progress more smoothly. This integrated perspective fosters a collaborative environment where specialists appreciate how their unique expertise fits into the broader data ecosystem. Perhaps most importantly, systems thinking transforms how data scientists approach problem definition. Rather than accepting problems as initially framed, systems thinkers explore the broader context, questioning assumptions and considering alternative formulations that might lead to more effective solutions. This more expansive approach to problem identification often reveals opportunities that might be missed with a narrower perspective. As the data landscape continues to evolve rapidly, systems thinking provides a crucial advantage in navigating change. By understanding the fundamental principles that unite different data domains, systems thinkers can more easily adapt to new tools and techniques, evaluating innovations within the context of their broader knowledge framework, rather than as isolated novelties to be mastered. This adaptability becomes increasingly valuable as the pace of technological change accelerates. Navigating the evolving data landscape demands more than keeping up with new tools. It requires a strategic approach to skill development. The adaptability that systems thinking provides is valuable, but how do you systematically build that capacity when facing thousands of courses, tutorials, and technologies competing for your attention? Most aspiring data scientists find themselves trapped in an endless cycle of learning never quite sure if they've learned enough to take the leap into their first professional role. This uncertainty stems from a fundamental problem: the absence of a personalized roadmap. Without clear direction, many fall into the trap of pursuing breadth over depth, accumulating superficial knowledge across dozens of technologies rather than mastering core competencies. The path forward isn't about learning more, it's about learning strategically, with intention and structure. Creating a personalized learning roadmap begins with honest self-assessment. Consider your current position within each level of Bloom's taxonomy across different data science domains. Can you explain statistical concepts like hypothesis testing to someone unfamiliar with the field? Are you able to apply programming knowledge to build solutions from scratch? Can you evaluate the effectiveness of different machine learning approaches for specific business problems? This assessment reveals where you stand on the continuum from novice to expert in each area. Map your skills visually, perhaps using a radar chart with axes representing different domains like statistics, programming, machine learning, and communication. The resulting shape reveals your current skill profile, where you're strong and where gaps exist. What's particularly valuable about this approach is how it highlights the difference between perceived and actual competence. Many aspiring data scientists overestimate their abilities in familiar areas while underestimating the importance of domains they've neglected. This clear visualization serves as both a reality check and motivational tool. Once you've created this skill profile, the next step involves prioritization. Not all skills demand equal attention. Your roadmap should emphasize developing depth in foundational areas before pursuing breadth across the entire field. This is where the concept of T-shaped skill development becomes particularly valuable. T-shaped development focuses on cultivating deep expertise in one or two core areas while maintaining sufficient breadth across related domains. The vertical bar of the T represents your specialized knowledge, perhaps in statistical analysis, machine learning algorithms, or data visualization. The horizontal bar represents broader understanding across the data science ecosystem, allowing you to collaborate effectively with specialists from other areas. This approach resolves the common tension between specialization and versatility. Rather than attempting to master everything simultaneously, you prioritize depth in areas aligned with your career aspirations while developing functional literacy in adjacent fields. A machine learning specialist, for instance, needs deep expertise in algorithms and model development while maintaining working knowledge of data engineering and business strategy. Creating concrete milestones transforms this abstract framework into an actionable plan. Effective milestones should be specific, measurable, and tied to demonstrable skills rather than completion of courses. Instead of finish a Python course, a better milestone might be build a data cleaning pipeline that handles missing values and outliers automatically. These milestones should follow a logical progression through Bloom's levels. Initial goals might focus on knowledge acquisition and comprehension, defining key terms, explaining concepts, and recognizing appropriate uses of different techniques. Intermediate milestones emphasize application and analysis, implementing algorithms, comparing approaches, and troubleshooting issues. Advanced goals center on synthesis and evaluation, combining techniques creatively, assessing limitations, and making strategic recommendations. For instance, if improving your machine learning skills represents a priority, your progression might look like this. At the knowledge and comprehension levels, you might focus on understanding the theoretical foundations of common algorithms. Your milestone could involve explaining how random forests work and when they're appropriate to use. At the application and analysis levels, you might implement these algorithms on real datasets, comparing their performance under different conditions. Your milestone could be building a classification model that predicts customer churn with specific performance metrics. At the synthesis and evaluation levels, you might combine multiple algorithms into an ensemble approach and critically assess the business impact of your model. Your milestone might involve developing a complete solution that not only predicts outcomes but also generates actionable recommendations. This structured progression ensures that your learning builds systematically rather than haphazardly. Each milestone represents a meaningful step toward mastery with clear criteria for achievement. The reality of this journey, however, is that motivation will fluctuate. Data science skill development requires sustained effort over months or even years. Maintaining momentum through this process demands deliberate strategies. One effective approach involves connecting abstract learning to concrete projects that matter to you personally. Rather than learning statistical concepts in isolation, apply them to questions you find genuinely interesting. Analyze your own financial data to understand spending patterns. Build recommendation systems for movies you enjoy. Use natural language processing to analyze books by your favorite authors. Personal relevance transforms learning from obligation to exploration. Another strategy involves cultivating a community of fellow learners. Regular interaction with peers facing similar challenges provides accountability, encouragement, and opportunities for collaborative problem solving. This community might take the form of study groups, online forums, or local meetups. The key is consistent engagement with others who can celebrate your progress and help troubleshoot obstacles. Perhaps most importantly, your roadmap should incorporate regular reflection and revision. As you develop new skills and gain clearer understanding of the field, your goals and priorities may shift. Schedule periodic reviews of your roadmap, perhaps quarterly, to assess progress, adjust priorities, and refine your approach. This flexibility ensures your development path remains aligned with evolving career aspirations and industry demands. What makes this personalized approach so powerful is how it transforms the overwhelming array of learning options into a coherent progression. Instead of jumping between unrelated tutorials based on passing interests, you select learning resources that specifically address your identified skill gaps and advance you toward concrete milestones. This strategic focus dramatically increases learning efficiency. Rather than spreading attention thinly across dozens of technologies, you concentrate effort where it yields maximum benefit. The result is deeper understanding developed more quickly, creating a virtuous cycle where each new concept builds upon a solid foundation. The question of when you're ready to apply for your first data science position becomes much clearer with this roadmap in place. Your readiness isn't determined by an arbitrary checklist of technologies or completion of specific courses. Instead, it's evidenced by your ability to complete increasingly complex projects independently, demonstrating practical mastery across multiple levels of Bloom's taxonomy. A good rule of thumb: you're ready to apply when you can confidently build end-to-end solutions that deliver value, even if they're not perfect. If you can take a business problem, translate it into a data question, implement an appropriate analytical approach, evaluate your results critically, and communicate your findings effectively, even on a small scale, you've developed the core competencies employers value. Remember that your first position will likely specialize in one area rather than requiring expertise across the entire field. Your roadmap should help you identify which specialized roles align with your skill profile. If you've developed depth in statistical analysis and data visualization, data analyst positions might represent your ideal entry point. If your strength lies in building and deploying models, machine learning engineering roles might be more appropriate. Landing your first specialized position marks the beginning of an exciting journey, but what truly separates thriving data scientists from those who merely survive? The answer isn't found in mastering today's hottest tools, but in developing a fundamental capacity that transforms how you approach every challenge in this rapidly shifting landscape. In data science, where technical skills can become outdated in as little as 18 months, continuous learning isn't just a nice to have, it's essential for career longevity. The complete data scientist isn't someone who knows everything, but rather someone who has developed systems for ongoing growth and adaptation in a field that's constantly in flux. This balancing act between depth, breadth, and currency presents one of the most significant challenges for data professionals at all levels. How do you maintain cutting-edge expertise in your specialization while simultaneously keeping aware of developments across the broader field? And how do you do this without falling into the trap of chasing every new tool or framework that emerges? The key lies in developing a strategic approach to continuous learning that prioritizes understanding core principles over superficial tool knowledge. When you grasp the fundamental concepts behind different techniques, you can quickly adapt to new implementations without having to relearn everything from scratch. Think of it as the difference between memorizing phrases in a foreign language versus learning the grammar rules. The latter allows you to construct novel sentences you've never heard before. Successful data scientists develop filters for evaluating which new developments truly warrant their attention. Not every new library, tool, or methodology deserves your immediate investment of time and energy. Before diving into the latest trend, ask yourself, does this represent a fundamental advancement in how we approach problems, or is it merely an incremental improvement? Will this still be relevant in a year or two, or is it likely to be superseded by something else? Consider how you might evaluate new machine learning frameworks. Rather than immediately learning every detail of implementation, first understand what problem the framework is solving and how it differs conceptually from existing approaches. This conceptual understanding allows you to make informed decisions about whether it's worth your time to develop deeper expertise. Online resources like MOOCs, tutorials, and video content have democratized access to cutting-edge knowledge in data science. Platforms such as Coursera, edX, and YouTube offer up-to-date content on emerging technologies and methodologies, making it possible to stay current without formal education programs. However, consumption without application leads to the illusion of learning rather than actual skill development. The most effective continuous learners don't just passively consume content, they actively engage with new ideas through practical application. When encountering a new technique or tool, try implementing it on a familiar dataset or problem. This hands-on approach will quickly reveal whether the new method offers genuine advantages and will cement your understanding in a way that passive learning never could. Beyond individual study, the data science community offers powerful accelerators for growth. Networking with peers through forums, social media, and local meetups provides insights into which tools and techniques are gaining traction in the industry. These communities serve as living knowledge repositories, allowing you to tap into the collective experience of thousands of practitioners facing similar challenges. One particularly effective approach involves building or joining learning communities focused on collaborative projects. A notable case study from the data science community illustrates this perfectly. A group of data scientists collaborated on analyzing sports performance data, sharing their findings through online forums and social media. This collaboration not only improved their individual skills, but contributed valuable insights to the broader community. Such collaborative efforts create multiplicative learning effects, where each participant benefits from the diverse perspectives and expertise of the entire group. Mentorship also plays a crucial role in continuous growth. Experienced professionals can guide newcomers through the complexities of the field, helping them navigate the vast array of tools and techniques available. Having a mentor who has already traveled the path you're on can help you avoid common pitfalls and focus your learning efforts on what truly matters. When assessing whether a new technology represents a fundamental change worth investing time in or merely a passing trend, consider its underlying principles. Fundamental changes often involve significant advancements in algorithms or methodologies that improve predictive accuracy or efficiency, while passing trends may include temporary fads that don't have lasting impacts. By focusing on the principles rather than just the implementation details, you develop the discernment necessary to make wise investments of your learning time. This principle-focused approach to continuous learning enables you to integrate new knowledge efficiently into your existing mental models. Rather than treating each new concept as an isolated bit of information, look for connections to what you already know. How does this new approach relate to techniques you've already mastered? What problems does it solve that previous methods couldn't address? By actively seeking these connections, you build a more robust and flexible understanding of the data science landscape. Consider keeping a learning journal where you not only document new concepts you encounter, but explicitly map how they connect to your existing knowledge. This practice of active integration helps transform isolated facts into a coherent mental model that evolves as you learn. The strongest data scientists don't have fragmented knowledge. They possess interconnected webs of understanding that allow them to draw insights across domains. Time management becomes increasingly important as your career progresses and your responsibilities expand. Rather than trying to learn everything, develop a personal curriculum that aligns with your career goals and interests. This might include setting aside regular time blocks for learning, perhaps dedicating one evening a week to exploring a new concept or technique. Consistency often proves more valuable than sporadic, intense study sessions. The question of depth versus breadth presents an ongoing tension in data science learning. While specialization remains important, the most adaptable professionals maintain awareness across multiple domains. Consider adopting an approach where you develop deep expertise in your primary specialization while maintaining sufficient breadth to collaborate effectively with specialists in adjacent areas. This balanced approach ensures you remain valuable in your core domain while retaining the flexibility to pivot as the field evolves. A powerful strategy for efficient learning involves focusing on transferable skills and concepts rather than platform-specific implementations. For example, understanding the statistical principles behind different machine learning algorithms will serve you better in the long run than memorizing the specific parameter names used in a particular library. When tools inevitably change, these transferable concepts remain relevant. Another effective approach involves learning in public, sharing your insights, code, and projects through blogs, social media, or code repositories. This practice not only solidifies your understanding through the act of teaching others, but also connects you with like-minded professionals who can offer feedback and alternative perspectives. The vulnerability of putting your work out for public consumption can be uncomfortable at first, but it often accelerates learning through the feedback it generates. As your career progresses, you'll likely find that your learning becomes increasingly self-directed and problem-driven. Rather than following predetermined curricula, you'll identify specific knowledge gaps based on the challenges you face and seek out resources to address those gaps. This just-in-time learning approach proves far more efficient than trying to learn everything up front. So where does this journey ultimately lead us? To become a true data head isn't about collecting certificates or mastering every new framework. As Kenji wisely points out, data science is not just about learning tools, it's about applying them to solve real problems. This perspective shift is transformative. The learning path we've outlined through Bloom's taxonomy provides something far more valuable than discrete skills. It builds your capacity to adapt and grow alongside this rapidly evolving field. When you approach data science with curiosity first, as Alex Gutman suggests, you naturally ask better questions and develop the mindset that drives meaningful innovation. Your data science journey never truly ends, and that's the beauty of it. The foundation you're building today will support a lifetime of discovery tomorrow.